Hello, hello students. To understand these topics, which is G parameters of laser cavity or stability curve or Gaussian beam or TM modes, okay, we need to know basically what are the basic modes or axial modes. Then only we can talk about the TM mode. Okay, so a wave of frequency nu, okay, that travels along the axis of the cavity forms a series of these standing waves within the cavity. Okay, so the laser modes governed by the axial dimension of the resonant cavity are basically called the longitudinal or axial modes. Right? And those determined by the cross-sectional dimension of the optical cavity are called as the transverse modes. Right? Now, this is basically my longitudinal traveling wave I could show, and in which we had a axial or longitudinal, and these are the transverse mode. Now, to understand this in a better position, what we did, we showed over here again same the transverse, the longitudinal, and this one is the fundamental transverse mode. Every time the first will be fundamental, and these two will be higher order, like when you have a different number of peaks, accordingly we'll get a higher order of transverse modes. Fine. Now next is this, I could show over here the dark region, okay, over here, and in between we get a bright spots. Now to understand the longitudinal mode more clearly, okay, we will go little back in a when we studied the cavity resonance frequency. Okay, so that time I had also told you that we had 4 types of cavity configuration. The first one I taught you was plane parallel, second was confocal, third was hemispherical, and fourth was long radius resonator. So when you take the first one, okay, what is the first one? The plane parallel. So what you have here, you have a cavity formed by the two plane parallel mirror, and the standing waves in the cavity, okay, was given by the equation. Which equation? The equation also we did this earlier in June. Okay, nu m was mc by 2 mu l. Okay, over here what was the mu? I told you mu was nothing but the number of half wavelengths or the axial modes that fits into the cavity. Fine. And each value of m defines an axial mode of the cavity. Okay, so therefore basically these axial modes, okay, basically these longitudinal or axial modes are formed by plane waves traveling along the laser cavity on a line joining centers of the mirrors and consist of large number of frequencies. Okay, so here I could show the separation, the frequency separation. So in this case, this is amplitude versus frequency. So the frequency separation, which is delta nu, okay, which I'll try and show it over here for you. So this is suppose my frequency separation. So this is given by C divided by 2L. Now what is this C divided by 2L? This one, C divided by 2L. So if you write nu m is equal to C divided by 2L, we are talking about this m, and what is left is 2 mu. Okay, so over here the frequency separation delta mu between the adjacent modes is delta nu. I'll write it again. Delta nu is equal to C divided by 2 mu L. Okay, so delta nu is basically independent of m. Earlier we had in the formula mc. Okay, this formula we had mc 2 mu L. Now all these axial modes contributes to a single spot of light in the laser output. Okay, that's what is the beauty of the axial or the longitudinal mode. Now to study the transverse mode, that is the actual we need to know. So as far as transverse modes are concerned, we need to understand the types also. Okay, so in transverse mode basically we have to understand the three types basically, which is one is TEM 00, then TEM 01 and TEM 11. So these three we want to study. So what is this TEM? We'll see first definition. So along with this axial mode, okay, the laser output basically is characterized by what is called as TEM or transverse electromagnetic modes. So they are few in numbers and easy to see, no problem in watching them or observing them. So if the laser beam is spread out by a negative lens and focused onto a screen, several bright patches, what I mentioned over here, several bright patches will be seen on the screen. Now the patches are separated by intervals called as the nodal lines. Okay, and within each patch the phase of the light is the same, but between patches the phase is obviously reversed. So the transverse modes characterize intensity distribution across the cross section of the laser beam. Okay, so modes are designated by, as I mentioned, they are given by TEM MN. Okay, now what is this MN? MN is basically integers, already we have shown you integers, and they represent the number of intensity minima in two orthogonal directions of the laser beam. This is important. What does this MN represent? Is this number what? So MN are basically integers and they represent a number of intensity minima in two orthogonal directions of the laser beam. Now the lowest order transverse mode is basically TEM 00. Now what it has got, how it looks like, it is like a Gaussian curve. So it has got a smooth cross-sectional profile with a peak in the middle. Okay, so I'll just show you how it looks like. So basically it looks like this. So this is my Gaussian beam. Okay, so this is my transverse mode, TEM mode with 00. TEM 00 is called as, and the beam pattern is like this. So in the center we'll see a bright spot. Okay, so in TEM 01, what is 0M has got? It has got a single minimum dividing the beam into two bright spot. Moment you say 01, we got a two bright spot. And as far as this 11 is concerned, 02 is not there for you, so we'll do 11. So for 11, actually what it happens, the beam has two perpendicular, this one and this one, two perpendicular minima dividing the beam into four quadrants. First with this horizontal one, it made two parts, with vertical two more parts. That's the reason we got this four quadrants by the TM11 beam has got two perpendicular minima dividing the beam into total four quadrants like this. Okay, so now after knowing this, we need to just quickly solve the two basic problems as far as to know how to understand or how to get the idea of the length or the number of modes is concerned. Okay, so the first problem we'll do is the half width. The first problem, the half width of the gain profile of a helium neon laser material is about 2 into 10 to the power minus 3 nanometers. This is half width. That is given to you, delta lambda. Fine. Now, what should be the maximum length of the cavity in order to have a single longitudinal mode oscillation. Okay, so as I mentioned, the formula already is known to you, so we'll write the formula first. The formula is delta lambda is equal to lambda square divided by 2 mu L. This is the formula to solve this. Now, in knowing what we need to get only single mode of oscillation. Okay, so with that logic, we'll take mu to be 1. Okay, so what we need to know now? We need to know length. So delta lambda is given to you, lambda is given to you. That's all we need. Fine. So we'll change the formula to L is equal to lambda square divided by 2 mu delta lambda. Now how much is lambda for HENE laser? It is 6328 angstrom unit square divided by 2 into mu is 1 and delta lambda they say 2 into 10 to the power minus 3 nanometers. So what should I write over here? Minus 3 and minus 9 gives you minus 12 meters. Even this is meters. Okay, so if you simplify this, okay, simplify and approximately you get the answer to be around 10 centimeter. This is the first problem. To take the second problem, what we'll write? The half width of the gain profile of a HENE laser material is about same 2 into 10 to the power minus 3 nanometers, so that they have not changed. Okay, 2 into 10 to the power minus 3 nanometers. If the length of the cavity is given, length of the cavity is 30 centimeter, how many longitudinal modes can be excited? That's the question. Okay, so the formula remains same. What we need to do first, find out delta lambda. So delta lambda is lambda square divided by 2 mu L. How much is lambda? As I mentioned, 6328 into 10 to the power minus 10 bracket square divided by 2 into mu is 1 into 30 centimeter. So I'll make it in meters. Okay, so if you simplify this, we should be getting the answer around 0.66 into 10 to the power minus 3 nanometers. Check it out. Okay, now we need number of modes also. So what is the formula to get number of modes? The formula is half width of the gain profile, half width of the gain profile divided by delta lambda. Fine. So half width is given to you, which is 2 into 10 to the power minus 3 nanometers divided by delta lambda is how much? We got the answer just now. It's 0.66 into 10 to the power minus 3 nanometers. So if you simplify this, this is 200 by 66, so almost around 3 number of modes you will be able to get it over here. Okay, so with this we at least got the idea of what is mode or what are axial modes and what are TEM modes. Okay, so next lecture we will be able to do what is the Gaussian beam and its properties along with the stability curve, which will end our second module 100%. Okay, go through it. Any difficulty, feel free to ask. Thank you very much.